It's really a very special pleasure to be here. As you mentioned, my father had taught at the Middle Eastern Technical University back in the 1960s. I don't remember that time. I was just a baby, but he talked very fondly of his time there. It was a very special time for him, and obviously, because of that, it's a very special time for me now. I've given these seminars hundreds of times perhaps around the world, but I must say this is a very unique experience for me, both because of that family connection, professional connection, as Professor Altan mentioned, but also because this is COVID-19, very strange time, very important time. And we are adapting, we are establishing this webinar with METU. I think that's very special. And I think some of the points that I will mention, and Professor Altan and I have talked before, we can potentially develop some solutions for COVID-19. So this is truly a very special experience for me, and I look forward to the discussion. I'm going to share the screen right now. I think you can see it. And this is the opening screen, Protein Electrodynamics in Terahertz Medicine, New Paradigms for Medicine in COVID-19. It is great that your organization has invited a diverse range of faculty from medicine, from MEMS, from physics, from chemistry, and so forth, because this is a very interdisciplinary field intrinsically. If there's one take-home message that you take away from this seminar, it's this image of this protein here in the corner that you can see vibrating. And that vibrating protein is the basic scientific principle underlying this concept of protein electrodynamics and terahertz medicine. And we will develop this idea of further experiments, results, implications, and so forth. So as I mentioned, it's personally a very special time. I actually posted on Facebook just yesterday that this seminar is 56 years in the making. My father was teaching lectures on nonlinear differential equations. 56 years later, I'm giving this seminar. And I said in my Facebook post, I think he would be proud. He is not alive, unfortunately, but I know he would be very, very happy about this. And so this is the announcement, as you saw, and this is his book, one of his books. He wrote 2 books at METU, Nonlinear Differential Equations. And you can see already 92 likes for this post. So it's gotten a lot of appreciation. So I want to start with a quote from Immanuel Kant, the German philosopher. 2 things fill my mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. It's a little bit strange to start off a seminar with this type of a quote, but I think it will make sense later. The starry heavens above and the moral law within. So this seminar is in 3 parts. I'll talk about some background, some science, and some applications with, of course, reference to COVID-19. In terms of background, we'll talk about the future of diagnosis, the future of therapy, the future of technology, and how does life work? These are the motivating questions that have been motivating me for a long time. Actually, this concept goes 3 decades. So let's talk about the future of diagnosis, specifically imaging. So you have the 4 modalities here: X-rays, ultrasound, PET, MRI, and CT, as you can see here. This is a timeline. Many of these are quite old. X-rays, as you know, are over 100 years old. But it's very interesting to note that ever since 1985, approximately, no new modalities have been developed since that time. You've had innovation of various sorts, such as diffusion MRI, multi-slice CT, PET-CT combinations, and so forth. But these are incremental innovations, not a fundamentally new modality. So one of the implications of this protein electrodynamics and terahertz medicine is the possibility of new ways of medical imaging. So the next concept is, what is the future of therapy? This is a chart of new drugs being developed as a function of research dollars going in. And as you can see, since the last half century, less new drugs with more money, there's been a monotonic decrease in the efficiency, as it were, of new therapies. And in fact, by the turn of the century, 2000, it costs about $1 billion to develop a new drug. So apart from incremental advances, innovation in some respect has also stalled on the therapeutic side. So whenever you see these types of, I teach innovation, these types of innovation blocks, if you will, one must be thinking about new paradigms. The third question is, what is the future of technology? And it's very difficult to predict the future, but in fact, in some respect, it's easy. There are some well-known patterns or evolution of technology. So for example, a landline, wired phones go to wireless phones and so forth. And so these patterns can be quite predictable, from immobile systems to ultimately force fields. For example, rigid steering evolving to electrical steering, a single leaf door evolving to a light lock. And we can say the same for medicine. Right now in medicine, we largely have what we would call a matter-on-matter interaction, where a drug has to bind physically to a protein, or a surgical device or the hands have to mechanically manipulate the target tissues. This is a matter-on-matter interaction. We can predict, in line with this predictable future of technology, an energy-on-matter interaction, where some form of energy will interact with proteins and function as drugs in that regard. This is a natural evolution. This will definitely happen. Of course, there are two questions: when will it happen, and what sorts of energies will be involved? And I will argue in this seminar that I think it will happen soon, if not now, and that it will be largely in the terahertz range that will make possible this new paradigm. The last question that's very motivating is, how does life work? This spaghetti-like diagram is what's called an interactome, an interaction map of the yeast proteome. In other words, which proteins are interacting with other proteins and how strong are those interactions, etc. It looks like a mess. And in fact, that mess results in the miracle we call life, which results from the current paradigm in terms of essentially random interactions and physical binding of proteins to each other. And to me, this has always been a mystery. How can this happen? Perhaps there are other mechanisms whereby proteins can sense each other from a distance, and this interactions can be mediated not just in a physical way, but perhaps in an electromagnetic way. So where do we go from here? What will be the future of medicine and healthcare? How can we better understand the fundamental mechanisms of life? Some of what I talk about today may lend some insights into these fundamental issues. So as I mentioned, the story begins over 30 years ago. Of course, the story of my connection to Middle Eastern Technical University was 56 years ago, but this story of this protein electrodynamics began over 30 years ago. And it began when I was an undergraduate at Harvard. I did my senior thesis with Professor Martin Karplus. Many of you may have recognized the name, of course. He got the Nobel Prize in 2013, and he was one of the pioneers of molecular dynamics and protein dynamics in particular. And when I was sitting in his office at his desk, I remember his words: proteins are neither solids nor liquids. They are something in between. I was very fascinated by that. And of course, that led to later results, as we'll talk about. So the second part of this will be, the bulk of this presentation will be about the science. And with respect to science, I'm going to talk about proteins. Most of you, of course, know about proteins, but I'll give a very quick review because we have a diverse audience. I'll talk about the axioms of protein electrodynamics, Terahertz medicine, protein dynamics, some scientific questions, electromagnetism and terahertz, some specific scientific results, conclusions, and technical challenges. So proteins, what do they look like? Proteins are macromolecules, large molecules of amino acids. Here on the left is myoglobin, mostly what we call alpha helix. And on the right is basic fibroblast growth factor, mostly beta strand. I've worked with both of these proteins. We have some other depictions of proteins, the androgen receptor, as well as human growth hormone. In addition to the ribbon diagrams you can see here, which depict the backbone, we see a van der Waals surface rendering of the protein as well. So what do these proteins do? They basically are the machinery of life. They are also the targets of many drugs, of course. And they range from structural proteins like collagen to storage proteins like myoglobin to transport proteins like hemoglobin, hormones, receptor proteins like the androgen receptor I showed you, contractile proteins like actin and myosin, which we'll talk about later, defensive proteins, the famous antibodies, of course, that everyone is hoping will be developed with a vaccine for COVID-19, and of course, enzymes which catalyze the metabolism of life. So obviously, proteins are very central to the functioning of life. So an example of a protein would be a transport protein like this voltage-dependent potassium channel. And the point of this picture here is to show you that this protein is undergoing two conformational states driven by molecular dynamics between an open state where the potassium ion can go in and a closed state where the potassium ion cannot go in. And this is a voltage-dependent potassium channel, which means fundamentally it is influenced by an electromagnetic field, not a terahertz field. But the point is it is influenced by an electromagnetic field by a change from a different voltage across the membrane. And that causes a structural shift in the protein. So that concept is very important. It is not a new concept. It is not a fantasy. It's not a science fiction. It happens in everyday life. The issue will be, as I will talk about in this seminar, how can we actually manipulate that using terahertz and subterahertz radiation. So the axioms of protein electrodynamics basically stipulate that proteins, as I've described them, emit and absorb electromagnetic radiation. And there are 5 axioms to protein electrodynamics. Number 1 is that proteins vibrate. That is what Martin Karplus showed us, as I mentioned. Number 2 is that proteins are charged. So here you see acetylcholinesterase, which binds the positively charged quaternary ammonium quaternary amine, acetylcholine. So there is a corresponding negative charge in the active site, and then there are positive charges around it. The mathematics, my father would know this better, of course, of the description of the static electromagnetic field around this is the Poisson-Boltzmann equation. But for electrodynamics, we have the Maxwell's equations, which describe, of course, the generation of electromagnetic radiation from moving or accelerating charges. And therefore, if proteins are vibrating, proteins are charged, and by the laws of electromagnetism, therefore, proteins will emit radiation. This is a paper that describes that. I'll talk about it in a little bit more detail later. And proteins must absorb electromagnetic radiation. Again, another paper I will describe later in the seminar. So the 5 axioms are: proteins vibrate, proteins are composed of charges, the laws of electromagnetism dictate the behavior of vibrating charges, and therefore proteins emit and absorb electromagnetic radiation. These are all facts, and we need to explore that. So Martin Karplus and others taught us that proteins vibrate, and this is the original paper from Nature in 1977 with Andy McCam and Bruce Gale and Martin Karplus focusing on bovine pancreatic trypsin inhibitor. And of course, much later in 2013, he won the Nobel Prize for being a pioneer in molecular dynamics, along with Michael Levitt at Stanford and Aryeh Warshel in Israel. So then the question is, if these proteins are vibrating, what are the frequencies of the vibrations? There are many papers about this, and I've selected one just to be illustrative in this regard. And this is from the Proceedings of the National Academy of Sciences with Jeremy Smith, also a good friend of mine, Christoph Kuzera, who is now at the University of Kansas, and Martin Karplus, studying myoglobin, the oxygen storage protein, comparing molecular dynamic simulations with neutron scattering, which is an experimental probe of this protein dynamics. So the theory, namely the simulations a la Karplus, are here, and the experiment is on the left. And you see these peaks that correspond to inverse centimeters, namely frequencies. And it turns out that about 15 to 20 inverse centimeters corresponds to 450 to 600 gigahertz, namely 0.45 to 0.6 terahertz. And that is the peak frequencies for this particular protein. What's important to note is that this is actually in what we would call the sub-terahertz range. Terahertz, as we'll talk about in a little more detail, has a wide range, but it is becoming increasingly evident that the relevant vibrations are in the sub-terahertz range. So what is the importance of this? Well, we all know that molecules vibrate, and in particular, of course, vibrations are manifest in the infrared range. All molecules have bond vibrations. And so for proteins, we have what would be termed low frequency motions in the terahertz and high frequency infrared motions. The motions and signals are different, and this table summarizes that. So low frequency, the type of motions would be those large scale subunit motions like I showed you in the potassium, the voltage dependent potassium channel. The infrared motions are going to be the very small motions, of course, of the backbone, the small groups of atoms, and individual bonds. Both of these spectra will be sensitive to conformational change. If the protein changes in a big way, like those shifts that I described, this spectral techniques, both spectral techniques will pick that up. And therefore, IR techniques are used in some forms of protein analysis. But the problem is that essentially, because we're talking about these bonds and what are essentially the same features for all proteins, infrared cannot be used to distinguish between different proteins. And because of that, the applicability potentially for medical diagnosis is not possible with infrared. It's possible in a research setting with very pure proteins and so forth, but it's not going to be possible in medical diagnosis. Now, when it comes to the functional significance of these motions, those little small IR-related motions are basically common to all proteins, but the very large scale, almost like nanomachine motions of proteins at the low frequency are the ones of functional significance. Therefore, terahertz is of functional significance. And if the point of therapeutics is to alter function, protein function, therefore terahertz will be more applicable to medical therapeutics. These are summarized in these pictures here. You see that infrared is sensitive to changes in the backbone atoms, but the differences between proteins will be washed out. You will see a signal in infrared of proteins, but all these proteins from myoglobin to lysozyme to insulin to fibrinogen to trypsin and so forth, they will all look largely the same. With terahertz, differences between proteins can become apparent. And this is a spectra of hemoglobin, myoglobin, an experiment that I performed with in collaboration, and I will discuss this spectra in more detail shortly. And large-scale motions are responsible for protein function. This is a Karplus paper that shows a wild-type Sark protein, an oncoprotein, and a mutant, and you can see that the motions are different, and I will also talk about this paper in more detail later. So this axioms of protein electrodynamics raise some scientific questions. Number one, do different proteins vibrate at different frequencies? The answer is categorically yes. Then the question is, can we identify different proteins based on this spectrum? The answer also is yes, but it's not easy, at least for now. And there are many reasons why it's not easy, and I'll talk about those during the course of this presentation. The answer to these two questions underlie the application to diagnosis. Then another question is the anharmonicity of the proteins significant? And the answer is may depend. Depends on the nature of the protein, depends on the solvent, of course, depends on the physical experiment probing those motions and so forth. If we can pump with energy, we might be able to minimize the anharmonicity and amplify the signal and so on and so forth. So this is an open question. Then we have some other questions. Can one influence protein function by modulating their vibrations? I think the answer is, in principle, yes, but the answer in reality is unknown. How far might the protein electromagnetic fields propagate? Some rough calculations say about 1 to 2 millimeters. Could protein electrodynamics mediate specific attractive forces between proteins? This is also unknown, but if you're familiar with van der Waals forces, of course, which are induced dipole interactions between atoms, you can imagine on a macromolecular scale an induced dipole, or more specifically an induced changing dipole between two proteins. It is a kind of van der Waals force, but it's not the same. We're not dealing with electrons within the atoms, we're dealing with whole scale motions. So the functional form of this type of an interaction will be an emerging force. It's obviously based on electromagnetism, but it will have a functional form like a London dispersion force or van der Waals force, but it will be different. It will be a new kind of force, but we don't know the answer to that. In principle, it should happen. Therefore, could proteins communicate over a distance? In other words, can they sense each other over a distance? And the answers to these questions will underlie that treatment. So many of you are familiar with this, but since we again have a diverse audience, I want to go over quickly what is terahertz. Terahertz, very simply, is the electromagnetic energies between the microwave on the low frequency side and infrared on the high frequency side. You can see that depicted here. And until recently, it was very difficult to engineer terahertz radiation as it lies between what are called the electronic and photonic domains of the spectrum. The electronic domain essentially uses unbound electrons, or the conducting band electrons to the technical term, to create electromagnetic radiation, while the photonics realm uses bound electrons or valence band electrons to produce radiation. You can imagine that the terahertz band is just between that, and that makes it very difficult. And essentially, you have to up frequency from the electronic side or down frequency from the photonic side to produce the radiation. But the irony, even though the engineering is difficult, is terahertz is all around us. It is emitted by living organisms, as we are all composed of proteins. And again, I show you that image of the vibrating protein. Also, it should be noted that terahertz waves are strongly absorbed by water, and this represents a significant challenge as well as an opportunity that I'll talk about. So in just some technical terms, this is the production of electromagnetic radiation to produce terahertz. This is power on the vertical axis, and this is frequency, and right here is 1 terahertz. And what this shows you is that on the electronic side, you have, this is a logarithmic scale, high power. On the photonic side, you have high power, but when you get down into the terahertz side, you have low power for the reasons that I described. And therefore, the terahertz gap actually represents a frontier in the electromagnetic spectrum. Some of you are experts. Professor Altan on the terahertz side are well aware of this. So that represents a true cutting edge in physics. There are also the opportunity to produce terahertz with free electron lasers, but that's not very practical for medical purposes. So what are the natural sources of terahertz radiation? I mentioned that the engineering is difficult, but the natural production is quite easy. And that's where I bring this quote from Immanuel Kant about the starry heavens above and the moral law within. The two natural sources of terahertz radiation are the cosmic microwave background, the residue of the Big Bang that created the universe, and that is a depiction of that. And in fact, 10 billion years ago, when the Big Bang was more recent and the cosmic microwave background was hotter, the peak was in the terahertz. And if there were human beings and scientists living 10 billion years ago, they would call it the cosmic terahertz background, not the cosmic microwave background. And because this is a black body, there is a tail that's actually terahertz, which is coming from the sky. And then the other source of terahertz is the moral law within, in other words, living organisms. And it may not exactly be moral law, but we know that to be human and to be living is to have some sort of moral sense. And so that's why I thought this quote is very relevant. Now, the NYPD actually uses this principle to detect guns at a distance. So they have a passive standoff detector that can detect terahertz radiation, which is naturally emitted by people, can penetrate clothing. The gun, the concealed weapon, is made of metal. It's not made of protein, so it's not going to emit the terahertz. So they can tell by a contrast. Most of you have gone to airports and have done those millimeter wave scanners. It's basically a similar principle that the body is emitting millimeter waves, which are of course somewhat lower frequency, but also relevant, but the gun is not doing that. So there are two key technical challenges to this concept. One is terahertz sources of sufficient power and spectral resolution. And the second is water absorption, which, as I mentioned, represents both an opportunity and challenge. If we can overcome these technical challenges, we can use terahertz for both diagnosis and therapy. Imaging, both anatomic imaging as well as functional spectroscopy, integrated together. Remember I mentioned about the need for a new modality. X-rays, MRI, ultrasound, PET, they all are based on physical principles. They don't actually probe the biology. Here would be an imaging that is probing the biological function during that time, the imaging. That's for medicine. We have a medical doctor in the audience who can fully appreciate that. For example, in myocardial infarction, the ability to see the functional significance and not just the anatomic lesion is extremely important. And of course, that's important not just in cardiology, but in many fields. Then on the therapy side, a form of protein-specific energy-based modulation. In other words, a device that acts like a drug. And that, as I mentioned, is the future of medicine. So the three principles, as I see it, of terahertz medicine are resonance with a protein function, localization, so it's a surgical form, if you will, not surgical cutting, but it's a localized therapy, and of course, of functional significance. Now, I want to talk about some experiments, and most of you are familiar with this, but we have two types of spectroscopy. We have what are called time domain spectroscopy and frequency domain spectroscopy. Time domain spectroscopy will blast a range of frequencies in a pulse, a broadband, wide range of frequency, excite the target, and radiation is given off of specific frequencies. We use a Fourier transform or other form of analysis to then dissect those frequencies. 99% of terahertz experiments, for various reasons that I will mention, are in time domain of measurements. And time domain is very elegant, very fast, and in fact, it's the principle of MRI. You blast the body with a radio frequency radiation, which excites various protons, and those proton spins will relax and be deconvoluted, as it were, spatially and in terms of frequency to give an MRI image. So these are time domain measurements. The other approach is frequency domain, using a specific frequency to sample the target tissues and then find out which frequencies are absorbed and which are not. It's a more laborious technique. In some ways, people regard it as less elegant, but one of my important arguments in this seminar is that we need to do, for biomedical applications, frequency domain measurements and not time domain measurements. So in other words, 99% of experiments that apply terahertz to biomedical applications are time domain, and they will have, how should I say, ambiguous or not very valuable results. Maybe useful, but not as useful as could be. So as I mentioned, I did some experiments while I was at Samsung in collaboration with Hanyang University in the Pohang Accelerator Lab. I worked with myoglobin, which is an oxygen storage protein, and hemoglobin, which is a larger oxygen transport protein. Hemoglobin has 4 subunits, myoglobin has 1 subunit. And this is the result I showed you earlier, which we'll look in more detail. It was a time domain experiment using a high intensity laser and what we call a femtosecond pulse. The sample was a powder, homogeneous pellet, path length 1 millimeter, very low humidity. We tried to really optimize the conditions. And this was the absorptions as a function related to control with no protein. And we studied these 3 proteins of bovine or cow hemoglobin, myoglobin, and human hemoglobin. So 3 proteins, red, green, and blue, as you can see here. The spectrum, to be very frank, does not look very impressive, but this is a very important result because many terahertz experiments with proteins showed a basically featureless spectrum. This spectrum has features, and I will go over some of the features. First of all, there's a difference between myoglobin and hemoglobin. At the slightly higher frequencies, the green myoglobin absorbs more than hemoglobin. Then you also see a species specificity, which is not attributable to artifact. In other words, bovine hemoglobin absorbs less than human hemoglobin at around 0.6, 0.65 terahertz. And then finally, we see negative absorption, which is, of course, emission or a Stokes shift at the lower frequency. So the protein is absorbing terahertz and spitting it out at a lower frequency, approximately around 0.2 terahertz. Now, as I said, as you saw, those features were quite minimal. They were definitely features, but not the type of spectrum that you might be useful if you've done infrared spectroscopy or NMR or so forth. But sharp protein resonances exist, and this is a study out of Buffalo with Dr. Andrea Merkels of lysozyme. Now, it's very interesting. Lysozyme is a quite rigid protein. It is a salivary protein that breaks down bacteria. It's a very rigid, solid protein. It doesn't have a lot of dynamics. It's designed to be solid in the external environment. And it actually, because of its rigidity, it actually crystallizes very well. And in college biology introductory classes, they might do crystallization of lysozyme. It's a very, very common protein. Because it forms such good crystals, Dr. Merkels and her team did terahertz experiments on these crystals, and you can see a fairly sharp resonance at 1.5 terahertz. That's slightly above the sub-terahertz range that I mentioned. And it might be due to the very rigid nature of the protein. And you'll see here degrees. These degrees are not temperature, but they are the angle of the crystal face with a polarized terahertz beam. So in other words, you see a sharp resonance when there's a certain alignment, presumably of the dipoles of the lysozyme with the terahertz beam. In other words, the sharp resonances exist, but we may need techniques, may not be crystallization, but other techniques which I'll talk about to extract those sharp resonances. Now, the reason I went into a little bit of a digression on the nature of lysozyme is that I actually do not believe it to be very electrodynamically active because of its rigidity, because it's not a kind of a regulatory protein. It doesn't have a lot of charges and so forth. But even though it's not very electrodynamically interesting, it does show this signal. Now, Professor Merkels' group followed up with additional studies of lysozyme to show the relation of these motions to biological functions. So in the normal case, there's a hinging motion with the transition dipole in this direction. When an inhibitor is bound, a drug, it changes the motion, so it's a more twisting motion, and the transition dipole shifts in this direction. So the motional characteristics shift with the functional status of the protein. And again, those motional characteristics are in the terahertz range in terms of their frequencies. So proteins also emit terahertz. I'll go through this one quickly, but Bacteriorhodopsin is a protein in the membrane. It's probably much more electrodynamically active than lysozyme. As I mentioned, it's more elongated. Has more charges. It responds to light. It's a proton pump. And so, in fact, it shows a terahertz peak at around 0.9 terahertz of emission of terahertz. Now, I should reference this paper by Martin Karplus, Molecular Dynamics and Protein Function. This is Sark protein, which is a oncoprotein. And you see these red marks is a very simplified way, easy way of showing the motion in a summary way, and we call that a heat map, which basically shows which regions of the protein are moving with greater amplitude and a function of the color red. And so you can see the wild type, which does not cause cancer, has a certain pattern of motion, and the mutation, which does cause cancer, has a different pattern of motion. So therefore, cancer proteins are different from normal proteins. And so conceivably, we can pick up diagnostically these different motions by virtue of their terahertz or sub-terahertz signal. Now, I also did collaborative studies with Ohio State, terahertz imaging of cancer, with Dr. Kubilay Sertel. He's also Turkish. He's a very prominent terahertz scientist. Professor Altan may know him. And we published, these are in proceedings, but we also published in the peer-reviewed literature, essentially comparison of optical microscopy with terahertz imaging, and I use the word very precisely, and we see differences between the normal and cancer tissue, absorption coefficient, so forth. And there are a number of other experiments, but I just wanted to summarize them here. I use the term imaging because this was a broadband time domain experiment. We're not looking at individual proteins. And Dr. Sertel and I have talked about the importance of doing continuous wave. But this experiment, as I mentioned, like many others, because of the nature of the limitations of the technology, is a broadband experiment. So we cannot, even though we detect a difference in cancer, it's more due to the overall water content and other features and not due to specific proteins. The ultimate vision would be to do some spectroscopic identification of individual proteins. So we decided also to do another target, namely Alzheimer's disease. And one reason why we studied Alzheimer's disease, as many of you know, it's characterized by the deposition of amyloid protein. It's a beta sheet protein. It forms regular structures. That amyloid protein eventually, to make a long story short, causes neuronal loss, neurochemical changes leading to dementia. So our hypothesis was that if these proteins are there, we might be able to pick up a terahertz signal. So we did, again, a broadband time domain spectroscopy. This was published last year. Reflection mode. We've formalin fixed paraffin samples. So this is not in situ, it's actually in vitro. Pathologic samples of normal and Alzheimer's disease AD hippocampus tissues from the brain. And we compared them with histopathology, and we also did, Professor Sertel did, he's a world expert in this, electromagnetic model of the myelinated axon. So the basic results, this is the optical microscopy, H&E stain, this is the terahertz image. We do percent ratio of reflectivity, and we quite see a significant difference, particularly in the white matter, of the Alzheimer's disease samples from the control sample. So that was quite a good result. And the implications were we saw a strong correlation between Alzheimer's disease and tissue image contrast. We want to refine the technology for different types of neurodegenerative changes. One interesting conclusion of general significance to doctors, not just terahertz scientists, is that the white matter changes may deserve deeper scrutiny and further neuropathological studies. And in fact, white matter has been observed to be an important part of Alzheimer's disease, which was previously thought to be just more death of nerve cells. The sensitivity to demyelination for this technique also just suggests applications to multiple sclerosis and other myelin disorders. But as I emphasize, continuous wave, not broadband, to obtain even greater specificity is based on the protein electrodynamics and terahertz concept might be an important way to continue. Another collaboration that I did was with the University of Texas, Dallas, with Dr. Kenneth O, who is an electronics engineer, and he developed an integrated terahertz source and sensor on a chip. The concept would be in the future, and I'll talk about this some more, to develop some sort of device that can do this sort of detection. So can one modulate protein function via terahertz? That was one of the questions that I outlined. This was a paper just from 3 days ago from a group in Riken in Japan, which I'm familiar with. Propagation of terahertz irradiation energy through aqueous layers, demolition of actin filaments in living cells. This is their experimental setup with a terahertz pulse. And this is the control, and this is the terahertz irradiated. So they see breakdown of the actin. They don't heat up the cell. They don't destroy the cell. This is not exactly the protein electrodynamics hypothesis. This is using a pulse. I think that using specific frequencies is going to result in much more interesting effects. Nevertheless, this was very encouraging, very interesting. People are starting to look at this as we speak, so to say. So the overall conclusions from this research, we have conclusions on the basis of proteins, tissues, applications, and technology. Number one, with respect to proteins, there are definite signals observed with proteins. Most low-frequency motions are in the sub-terahertz range. This is extremely important. Continuous wave tunable spectroscopy, therefore, may be better able to detect these. And one approach is 2D terahertz spectroscopy. I'm not showing the results, but this is work that I've done with MIT and Dr. Keith Nelson. Professor Altan may know him. And we have submitted, we've actually had a patent approved for this technique. On the level of tissues, different types of tissues can be distinguished via terahertz imaging, and presumably even more by the virtue of terahertz spectroscopy. Specifically, normal and pathological tissues can be distinguished, and we demonstrated applications in cancer and Alzheimer's disease. So in terms of applications, we have both imaging, specifically the water contrast, and spectroscopy focusing on proteins. And this would be an incredible technique because it's label-free, native, and non-ionizing. Most other techniques of spectroscopy involve, either labels or they're not native. You have to do some contrast or using the ionizing radiation. The technological implications are the premium on high power pulsed continuous wave or multi-frequency sources and detectors. The sources must be optimized for biomedical applications to the sub-terahertz range, and miniaturization via silicon-based CMOS platforms. How can we solve the water penetration problem? There are 4 ways that I think of. One is the range. If we focus more on the sub-terahertz for biomedical applications, so this is the absorption. The absorption in the water is much less in the sub-terahertz range than in terahertz. In fact, it increases here. So this is absorption, this is frequency, this is water. And you can see that we have less absorption in that sub-terahertz range. Tunability, if we can do continuous wave spectroscopy. So these are water windows. In other words, some water frequency is not homogeneous throughout. There are water windows. This is well established in the microwave spectrum, and there's strong evidence in the terahertz spectrum. Pulsed, not femtosecond pulse, but picosecond pulse, to minimize the water relaxation effects. So you want to put the terahertz through very quickly, and the reason for the absorption is you basically get absorbed by the hydrogen bonding water as a macromolecule. And there's some evidence that you can have 15% more penetration if you use these pulses. That's work out of Russia. And then higher power, of course, just by virtue of Beer-Lambert, it's exponential, but we can push radiation through. Based on this biology, back to the physics. So this is, as I mentioned, the electronics approach and the photonics approach. So in the electronic sources, we have solid state, we have vacuum, photonic sources, we have lasers, which is what I used in my studies, and electro-optical conversion. But as I mentioned, continuous wave is really critical. So the vacuum approaches are not so good on the electronic side. So I think the sweet spot technologically will be the solid state approaches, particularly using CMOS silicon-based approaches to produce continuous wave and high power as possible sources. So I'll finally end with some applications, and I'll go through this section very quickly because this is more some speculation and some ideas. And we'll talk about why, we'll talk about new medicine, what are the potential applications, Terahertz Light Switch, we'll talk about cancer, neuromodulation, bacteriorhodopsin, antibiotic resistant antibiotics, drug screening, protein-protein interaction, affinities, new paradigms of COVID-19, why now, quadcopter, and my book Waves. So as I mentioned, we need a fundamentally new approach to diagnosis and treatment. Medical imaging has had no new modalities. We need lack of specificity is a problem. Biopharma has been declining for half a century, unsustainable costs. Technology evolves, and as I said, the future will be a energy on matter approach. So energy on matter will be the future of medicine. Why? Greater specificity, more non-invasive, greater effectiveness, lower cost, more rapid therapy development, convergence of medicine and surgery. And this is happening now, maybe not in terahertz, but in other areas. Why it is time to take electrified medicine seriously on the cover of Time magazine. Google spin-off teams with pharma to treat disease by zapping nerves. This is the so-called electroceuticals. Galvani is a joint venture between Verily and GlaxoSmithKline. Bioelectrodynamics research team, Dr. Michal Shifra, a friend of mine out of Czech Republic. You can see here sub-terahertz, protein, control function. People are starting to do this, as I mentioned. So what are the potential applications? Cancer, I'll talk about this in a little more detail. Infectious diseases, Alzheimer's, wound healing, and many more. This is a platform technology that will revolutionize both diagnostic and therapeutic medicine. So let's start with some possible experiments. I think that one of the key experiments, one of the beautiful experiments that would demonstrate the power of this would be a so-called Terahertz Light Switch to control bioluminescence. Many of you know about these bioluminescent jellyfish, and this is the water of Australia. Beautiful scenes, and then of course fireflies, bioluminescent. How does that work? Well, it's a protein called luciferase, and this is the protein that through a complicated process that I'm not going to discuss here, produces this light. If you can control that light production through terahertz, as I mentioned, or sub-terahertz, you would have a light switch. So you have a cell-free bioluminescent extract, terahertz frequency scanning experiment, observe for on-off effect. We basically see the light turn on and off. You correlate with molecular dynamics simulations. My friend, Professor Ho Leung Ning, who was also a student with Martin Karplus, now at Kansas State University, is interested in working on this. What about cancer and microtubules, electromagnetic Taxol? I don't know if you can see this. Well, this was supposed to be a video, but anyway, what this is microtubules are proteins that control the division of cells, and cancer is too much division of cells. So the most powerful medicine is called Taxol. It inhibits the polymerization, or actually inhibits the depolymerization of these microtubules, preventing division. The problem with Taxol, it's very powerful, but it also affects normal cells. We have cells in the skin, we have cells in the gut, we have cells in the bone marrow that are dividing, and the Taxol has these toxic effects. But if we can electromagnetically, in a focused way, affect these microtubules, that would be an electromagnetic approach to cancer treatment. So Dr. Haben Su and I have discussed this. He was at NTU in Singapore, now in Hong Kong. This would be the experimental protocol. Neuromodulation. As you may have noticed, I have a honorary fellowship at the University of Melbourne, and Dr. Stan Skafidas for neuromodulation. He's bioprinted or 3D printed a cortex. If we can see terahertz to affect the nervous system development, there might be some interesting applications there. I mentioned Bacteriorhodopsin as a proton pump. This is Professor Fadel Samate, also a friend of mine, was at the ILL. Proton pump switch. There could be biocomputing applications. Now, a big problem, we have COVID as a problem, but another problem is bacteria. Bacteria usually are not a problem because we have antibiotics. One reason why COVID and other viruses are a problem is we don't have drugs that kill viruses, and I'll explain why shortly. But we have drugs that kill bacteria, so nobody is worried about bacteria. But what if you have antibiotic resistance, a post-antibiotic era? This would be not an apocalyptic fantasy, a very real possibility for the 21st century. 5 years from now, we could have antibiotic resistance bacteria, and COVID would look like kindergarten compared to what that could be. So we need to develop more low-cost, resistant antibiotic therapy. The problem with antibiotics is they're drugs, so the bacteria become resistant. We have to develop a new drug, takes many years, and so forth. These drugs act on the cell wall synthesis, protein synthesis. These drugs act on proteins. But if we had an electromagnetic approach and it became resistant, basically we would tune the frequency slightly differently. So we could catch up to the bacteria instead of always being behind in case the situation occurs. So I had discussions with Institut Pasteur about, they have a high throughput drug screening program, robotic. but instead of testing drugs, we could test different terahertz frequencies to develop this concept. Protein-protein interaction affinities using techniques also in discussion with the Institut Pasteur to answer these questions of these electromagnetic attractive forces. And now I'll talk a little bit about COVID. What is a virus? A virus is a genetic material contained within an organic particle that invades living cells and uses the host metabolic machinery to produce new virus particles. In this colorized photo, you see the yellow virus, you see the cell here. The question is, are viruses alive? And I'll answer that question quickly or shortly. So the virus has three parts from the inside to the outside. It has a nucleic acid on the inside, it has a lipid membrane around that, and then finally it has a spike protein, many of you are familiar with this, on the surface. And the nucleic acid is responsible for the genetic material. The lipid envelope determines the environmental viability. So soap and alcohol work, and the spike protein, very important, determines the target. It's blocked by antibodies and also used for testing. So this protein is very unique on this COVID. One of the questions is, as I mentioned, are viruses alive? The answer is no. You cannot use antibiotics for viruses. There are only two ways to get rid of the virus, either to physically destroy it or to have it cleared by the immune system. Antibiotics cannot kill it. So if we had some sort of treatment to prevent it, it would have to interfere with that binding of the spike protein to the target of the cells. So most of you have seen a handheld thermal scanner that detects infrared radiation. One concept is to have a handheld COVID scanner that could look on the patient or in the mouth and see a signal related to that COVID-19 spike protein. Now, you know, President Trump was famously talking about putting UV light in the body and disinfectant and so forth. I want to tell you something very interesting. Many people thought that was a very stupid comment, and I think he expressed it, you know, very strangely and so forth. But I was listening very carefully. I don't think the video works, but it's okay. Most of you are familiar with that. But if you can use terahertz for medical purposes, you can probably also use it for military purposes. If you want to stop a protein, you could use it not just to cure disease, but you could use it to kill people. And when I watched that press conference, I was very fascinated because the president gets a lot of briefings from national security and all that. He has access to information that you and I don't. But I do know that terahertz is being used and developed for military purposes. And he probably had some sort of briefing where people were talking, well, we're developing these things, you know, everyone is panicking. Can we possibly use this for COVID? And so when he was talking, if you listen very carefully, he was saying, we're working on that with this, you know, electromagnetic radiation and so forth. And he was not very knowledgeable and not very scientific, but people were probably talking about it, and he was probably revealing a lot more secrets than most people realize. But anyway, back to the point, the concept is that there may be electromagnetic, specifically terahertz approaches for eliminating the virus or inhibiting the virus. So terahertz physics has been a challenge, but why now? There's growing interest, more research, thanks to Professor Altan and others. Terahertz market growing tremendously, even without biomedical industry. It's becoming mainstream in medical and industrial. Better performance, successful miniaturization, and extremely importantly, decreasing costs. The use of metamaterials and graphene promises to drive down costs even more. Professor Altan has talked about that. So Star Trek tricorder, many of you are aware that science fiction can inspire the future. This is the communicator from Star Trek, and of course that led to the mobile phone or inspired that. We have the tricorder, the famous tricorder with Mr. Spock and so forth. But I actually think the concept could be even more with a quadcorder, because the tricorder, if you remember, was just diagnostic. Captain Kirk, Scotty, Bones, the doctor, can you tell us if there's a living life form behind that rock? He pulls out his tricorder, he says, yes, Captain Kirk, there's living life form behind that rock. but they don't do treatment with the tricorder. But terahertz, in the concept that I'm explaining, could also be therapeutically oriented. So therefore, I think we could call this a quadcorder. There's more than just technology. I've actually written a book in addition to this research called Waves. It's on Amazon. And it is a description of this technology in a literary setting. It explores the good and evil and all the social aspects of this. So as I said, it could be both military and medical, and there's a story around all of this. So because this is a paradigm shift, it will involve not just scientific papers, but whole social engagement to make this happen. There's another reason for this book. I published this in 2009, and it puts in the public domain the concept that proteins can be detected or modulated using terahertz radiation. This is extremely important. The reason I did this was that nobody can patent this central idea. Anybody is free to develop technology around this idea. So if Amazon or Google patents this idea about proteins being modulated by terahertz radiation, forget about it. Ogan Gorel has already exposed that in the public domain. Google, Mark Zuckerberg, whatever, they cannot dominate this that way. And that's very important because I also study startups and innovation. And one of the reasons why startups fail is they often don't have freedom to operate. Now, you might also say that's very foolish. Oh, you can't patent it, so you can't get any investment. You can patent individual implementation. You can patent the individual sort of instrumentation or devices, but you cannot, nobody can patent, including METU and so forth. Nobody can patent this central idea. And I think that's extremely important and extremely beneficial. And that was the reason for the book. So some closing thoughts. I've talked about this in the Americas, North America. I've talked about this in Europe, in Asia, Australia, and now today in Turkey. So this, I've talked about it in many places, but this is a very special time, as I mentioned. Isaac Newton, who's the founder of physics, this is his Principia, wrote, these are the last lines to the Principia, the general scholium, at the very end of the Principia. Most people think he's, of course, the founder of physics, but he was very interested in biology. He talks about the vibrations of the spirits propagated to the fibers of the nerves, from the brain to the muscles, but these things cannot be explained in a few words. Not a sufficient number of experiments to determine and demonstrate accurately the laws by which this electric and elastic spirit operates. Those are the last words of the Principia. Of course, he's not thinking about proteins, but I love those words, this electric and elastic spirit, because I think it encapsulates this concept. One of my other heroes is Richard Feynman. I would study his books, lectures on physics. All of you are familiar. And in his third lecture, in the first book, he writes, everything that living things do can be understood in terms of the jigglings and wigglings of atoms. So it's a little bit more American English than Newton, but it's a very similar idea. And finally, I attended Martin Karplas's October Nobel Prize Celebration Symposium. Many of his former students, myself included, gave short seminars. So I presented this idea, and he was in the front listening. Of course, there were other people. And I asked him at the reception, Professor Karplas, what would you suggest? And he said something very interesting. Remember, he is one of the world's foremost computational chemists, one of the world's foremost leading theoretical chemists. He didn't say do calculation. He said, I would do an experiment on an enzyme. If it works, it would be significant. Those were his words. And I thought that was very interesting, both because of terahertz and all that, but I also thought it was interesting because it was a testament to his intellectual strength that he recognized the limits of his own sort of ideas, that computation probably would not solve this problem. It had to be an experiment because electrodynamics combined with the dynamics and the solvent and all this are just too complicated. So that is my hope with METU, that we can do some key experiments to answer some of these questions and potentially develop some of the applications that would have a real impact. So in the beginning, technology is not always pretty. So I showed you those spectra. They didn't look very impressive. This is not very impressive, but dreams can fly, moonshots can become reality, and even Mars shots. So as we say in Korea, kamsamida, çok teşekkür ederim, as we say in Turkey. Happy to answer any questions. I'm on LinkedIn, and you can also reach me by email.
Thank you very much.
Thank you very much.
Thank you very much, Dr. Gura. Very, very interesting discussion. You know, if the audience has any questions, we can take them now for Dr. Gura. I have a couple, but I'll wait for others to see if anyone wants to make a comment.